The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so last time we talked about nonlinear dynamics. We drew phase plots. We talked about basins of attraction. We talked about fixed points. And we hinted at control, right? And I tried to motivate control not as some nice matrix manipulation of equations, but actually by thinking about phase plots and saying you're gonna move that phase plot a little bit. You're gonna reshape it in order to bend the system to your will, right? But just a little bending, right? You're only allowed a little bending in this class. Okay, so today we're gonna make good on that idea, but we're gonna do it on an even simpler system first, just today. We're gonna do it on the double integrator, which is Q double dot equals U, okay? Because here I can do everything analytically on the board, okay? If you want a physical interpretation of that, which I always like, you can think of this as a brick of unit mass on ice, where you provide as a control input a force like this. Maybe the force equals U, and there's no friction, and mass equals 1. Okay? What we're going to try to do with this double integrator is roughly we're going to try to drive it to the origin. We're going to try to drive it to zero position. I guess that's negative x in this picture, and with 0 velocity. Okay? It turns out there's lots of ways to do that. And the goal here is to make you think about ways to do that involve invoking optimality, because that's going to be our computational crutch for the rest of the term. Okay, so I've been trying to bring the tools from the different disciplines all together. So let me start by doing just a quick sort of pole placement analysis for those of you that don't think about poles and linear systems that much. So if I want to write a state space form of this equation, again, I've always tried to use Q just to be my coordinates, and I'll use X to be a state vector. So a state space form of this. It's going to use the vector X to be, in this case, Q and Q dot. Okay? And that dynamics there is the simplest state space form you're going to see, but a state space linear equation will have the form AX plus BU. In our case, it's going to be the trivial 0, 1, 0, 0 times x plus 0, 1 times u, right? Okay, it's not going to get easier than that, but we're going to use that form because that's going to help. Okay, our goal now is to design u, right? We want to come up with a control action u, which you can think of as being a force on the brick, let's say, which drives the system to 0. So in general, our goal is to design some feedback law. I use pi for my control policies, which is a function of x. Okay. Let's start by doing the linear thing. Let's start with considering u's of the form negative kx, okay? Where k is a matrix. Well, actually, what is k in this case? 1 by 2, right? So it's going to be k1, k2 times x, which is my q dot. Equivalent to saying negative k1 q minus k2 q dot. So many of you will recognize this as the as a proportional derivative controller form. Okay. Okay, so if I take this u equals negative kx and I start thinking about what if I change k, what happens to my control system, that's easy to do in linear systems. So if I stick that gain matrix in, then what I get is a closed loop system, which is a minus b k x, right? Which is just the system 0, 1, negative k1, negative k2, x. Okay, and if you've had a class on differential equations, you know how to solve that. Right, the solution uses the eigenvalues of this system. You can quickly take the eigenvalues of that matrix. Characteristic equation works out to be k squared minus 4k1 all over 2. Okay, with eigenvectors v1 is this, v2 is this. Okay, that's just the eigenvalues and eigenvectors of this matrix. Okay? Okay, so what are the conditions on the eigenvalues to make sure the system is stable? You want them to be both negative, okay? And we also, potentially, we care about whether the system has any oscillations or not, which manifest themselves on whether the thing's complex, got complex eigenvalues, right? This is all things you've seen in plenty of classes, but the only way it's going to be complex is if this thing goes negative, right? Okay, so we want a couple things, right? We want both of them to be, both of these to be less than 0, which we can get pretty easily, and we want k2 squared to be bigger than 4k1, right? K2 squared is bigger than 4k1, then the system is actually overdamped. If it equals 4k1, it's critically damped. And it's underdamped if it's less than 4k1. And we want, for stability, we want lambda 1 and 2 to be less than 0 for stability. Okay, so just to connect this to the phase plots we were talking about yesterday, you might have seen phase plots first in this context, in the linear systems context. The reason to do this eigenvalue decomposition is that you have these beautiful graphical interpretations of the solutions to the system. Let's choose a particular case. What did I pick? Oh yeah, so let's say K1 is 1. That means I'm going to want to think about an overdamped system. I want K2 to be at least greater than 2. So let me make it so I'm going to choose K2 equals 4. If I do that, then my eigenvalues work out to be negative 4 plus or minus 16 minus 4 over 2, which is negative 2 plus or minus square root of 3. Square root of 3 is about 1.75. Okay, so I get negative 0.25 and negative 3.75 for my eigenvalues. Okay. And the eigenvectors are going to be just this form. So what that allows me to do is make my same state space plots we were making yesterday, where now I have Q and Q dot. Okay. And my first eigenvector is going to be 1, negative 0.25. Okay. So if I go, I'll use these as quarters. So I go minus 0.25, and the time I go 1 here. So I get a line that looks like this, right? That's V1. And I get a line that goes almost 1, negative 4, so a little bit under that here. V2 is over here. Okay. And the eigenvalues on this, if you've seen these plots before, we typically cartoon. They're both negative, so we're going to draw an arrow like this. Systems, initial conditions that start on this will just get smaller, right? Initial conditions that start on this will also get smaller, but they're going to actually get smaller a lot quicker. Just to say a few of the subtleties, right? So I chose an overdamped system so I don't have repeated eigenvalues, right? I chose a overdamped system so I don't have oscillations because I can't make the same plots. But for the overdamped system, this is a great way to think about things. The reason that when I don't have repeated eigenvalues, any initial condition of the system can be written as a linear combination. That means that when the system doesn't have repeated eigenvalues, the eigenvectors span the space. Okay. Any initial conditions can be written as a linear combination of the two eigenvalues. Okay. And the dynamics from this point are just the exponential dynamics of the two components. I don't know. Tell me if you want me to say that again in a more. It's not really the focus, but if you understand that, you got the whole thing here. So what it means is you could take any initial condition. It turns out any initial condition, when I have eigenvectors which span the space, I'm guaranteed to have that if I have unique eigenvalues. Then I can write this as a combination of these vectors. Okay, so I'll try to do it. I've got some sort of one component like this and one component like this. This initial condition, if I say this is x0, okay, and it turns out so I could say x0 is alpha 1 times v1 plus alpha 2 times v2. Okay, we know that initial conditions that are just on the line v1 go like e to the negative lambda, or e to the lambda t v1, so the whole system goes like alpha 1 e to the negative lambda, sorry, just got negative eigenvalues, to the lambda t v1 plus alpha 2 e to the lambda 2 t v2. Okay, that's the great thing about all these linear systems. So what that means is if I've drawn the eigenvectors, then I know exactly the entire phase plot of the system. Okay, so we're connecting it back to the pendulum. The pendulum I went through in all the different places. I thought about what the contributions were and mapped it out. Here I don't have to do that. I know that this system is the component that has in this eigenvalue is going to decay quickly towards 0. And it's going to decay faster than this one, which means an initial condition like this is going to go like this. I should have used one of my many other colors to do that. This looks like a blue. All right, so trajectories from that initial condition are going to do that. Okay? And trajectories from this initial condition are going to, what are they going to do? What if I start over here? They're going to go mostly down, and eventually we think it's stable, so it's going to get to the origin. I could even do my filled in circle there, okay? When are they going to start bending towards the origin?
Once it hits.
Later. They have to pass this before they can, right? They have to pass that and get to negative velocities before they can hook back in, okay? So the trajectories look like this. And go in, yeah? And likewise, so all these trajectories sort of, you can map out the entire phase portrait of the space pretty quickly just by understanding the eigenvalues and eigenvectors. Okay? The same thing's true over here. So it's okay, so just another example of a phase plot that we have. In the linear systems, it works out to be clean. You can just do these eigenvalues, eigenvectors. Okay, now control. We're allowed to change K1 and K2. Changing K1 and K2 is going to change the phase portrait, right? It's going to change those vectors. I want to change them to make it do whatever I want. So that's actually, the first discussion is what do we want to make it do, okay? Maybe even before that, I should observe that without thinking about optimality at all, it would be easy to sort of stop here, okay? Because if I look at this carefully, as long as I choose K2 squared greater than 4K1, I know I'm going to not oscillate, okay? And I can just start driving K1 and correspondingly K2 up as high as I like, right? And make the system get to the origin as fast as I want, and it won't oscillate, right? So what's my motive? Why would why not just drive them all the way to infinity?
You don't have a motor that can do that?
You don't have a motor to do. That's the first unsatisfying thing. Absolutely. Probably there's some unmodeled thing. Even if I did have a motor that could do that, there's probably some unmodeled things that I might excite and cause bad things to happen anyways. You could melt the ice on the brick. That's right. That's right. I guess I could have said wheels, and then maybe they'd melt the tires. Okay. And you can see that here, actually. Remember? So what does the unactuated phase plot of the system look like? I can just draw that. If U was just uniformly 0, if K1 and K2 were 0, what would the phase plot have looked like there?
Is that a circle? Oh no, but that's a constant.
It would have just been x dot equals A of x, where A is this guy, right? So it wouldn't have been as interesting, right? It would have been, every point would have just had a vector like this, right? It would have been a little bigger with bigger velocities, right? But it would just be a flow like that, which I hope is sort of what you'd expect it to do since it's an integrator, right? Things are just going to off into the ether. Okay, so if I consider I started with this, and I'm getting out things that look like this, I'm already, in my unitless cartoon here, it sort of already looks like I'm using a lot of torque to do what I'm doing, right? Or I'm using a lot of force, right? I'm really significantly changing those dynamics in order to bend this thing to come around like that. That's okay, but we can do better. Okay? So today, I want to use this system, which I think it's quite easy to have strong intuition for, to start designing optimal feedback controllers. Okay. So let's address the, we don't have infinite torque problem first. One more comment on this. So there's I didn't actually call them poles. There's a pole placement version of this too. It's exactly the same thing. If you were to draw a root locus, what would the system look like? In root locus, you would be changing, the typical root locus would be, you're multiplying the entire feedback by some linear term. You're not scaling them, in some squared law. So what you get is, for very small feedback gains, you get oscillations. As you crank it up, the poles connect in the left half plane, and then they separate, right? And as I keep turning up my gains, one of them creeps towards the origin, the other one goes off really far to infinity. Right? So just those of you who think about poles and zeros, this is exactly the same way to say that, right? I didn't do a root locus because I was changing two parameters, but it all connects, okay? Okay, so now let's say I have a hard constraint on what U I can provide, okay? Let's just say that I have an additional constraint let's say the absolute value of U has got to be less than 1. Okay? Well, that changes a lot of things. My linear system analysis is sort of impoverished now. I'm going to, if you want a graphical version of what that's doing, that's sort of, my zero input looked like that. I wanted to go like this with my linear controller, but maybe it's capped at something like this, right? Okay, so what's that going to do to your system? If I were to just take my U, if I just ran the policy U is some saturation, let's say on negative kx. I took my same linear feedback controller, and I just said, if it's greater than 1, it's 1. If it's less than negative 1, it's negative 1. I think you're still okay. Trajectories are still going to get to the origin. They might take fairly long routes to the origin, okay? You're not going to lose stability in this case because of that. But it starts to feel like, man, I should really be thinking about those hard constraints when I design my controller, okay? All right. So how do we do that? One way to do that is optimal control. It's not the only way to do it. Let's formulate an optimal control problem. Let me sync up with my notes so I don't go too far afield. Okay. Let's say my goal in life is to get to the origin as fast as possible in minimum time, okay? But I'm subject to this constraint, okay? So that's the famous minimum time problem. Subject to that constraint. Okay.
Are we trying to stop at the origin?
Yes. We want both the position and the velocity to be 0. Turns out you need this constraint for it to be a well-posed problem, right? If I didn't have constraints on U, then like I said, I would just use as much U as possible. I would get there infinitely fast, and we haven't learned a whole lot, okay? There are other ways to penalize U or something like that, but we're going to put a hard constraint on it here. Okay, now muster all your intuition about bricks on ice and tell me if I've got limited force to give and I want to get to the origin as fast as possible, what should I do?
Bang, bang.
Bang, bang. Okay, good. He knows the answer. What should I do? Who haven't thought about it and don't know what bang bang is?
Accelerate as much as possible and save as much as time we need to start up there.
Right, right. So if I want to get there as fast as possible, I'm going to hit the accelerator, go as fast as I can until some critical point where I'm going to hit the brakes, and I'm going to skid stop right into the goal, right? There's nothing better I can do than that. We're going to prove that, okay? But I want to see, that's a fairly complicated thing. It's something you can guess for the double integrator. You can't guess for a walking robot, for instance, okay? But we want to get that out of some machinery that's going to be more general than double integrators. Okay, so the proposition was bang, bang control. Okay, bang, bang control. You might hear people casually say bang, bang control is optimal, and that is, it's very common if you have hard limits on your actuators. It's very common that the best thing to do is to be at those limits all the time. Okay, if that's the way you've defined the problem, bang, bang control solutions are pretty ubiquitous. Okay. They don't always work that well on real robots because actuators don't like to produce infinite force and then, or max force and then negative max force within a single time step, but good. Okay, so I think the only subtle part about it is figuring out when I need to switch from hitting the gas to hitting the brakes. Okay, so let's see if we can figure that out first. I think a pretty good way to do it is to think about what happens if you hit the brakes. Okay, and then you want to hit the brakes and arrive directly at the goal. There's only going to be a handful of states from which if I was going at some position and some velocity, and I hit the brakes full now, I'm going to land exactly at the goal. Let's see if we can figure out that set of states first. Okay, so let's think about the case where Q is greater than 0 first, just pick a side. Okay, so in that case, hitting the brakes, is that +1 or -1? -1. No, it's +1. Sorry, you almost got me. If Q is greater than 0, it's positive. If Q is greater than 0, then U is +1. All right, I want to be pushing back in the direction I'm already coming from. Right? So U is +1. Okay. All right, so now we're going to have some math ahead of us. See if we can integrate this equation. Okay. I can do that on the board for you. Q dot of t, I better get it right, is yeah, U of t, so in this case it was 1, plus Q dot of 0, right? I'll just make it a little bit more general here. In this case it was 1, okay, and Q double dot of t is, sorry to switch orders, Q0 plus Q dot 0 t plus 1/2 ut squared, right? Okay, I want to figure out, did I screw it up? What?
Just in the label. Just in the label. The first symbol is.
Oh, sorry, thank you, good. Thank you. Okay, so let's figure out if U is 1, what trajectories are going to get me so that Q at some t final, qt and q dot of t are 0. Okay, simple enough. Little manipulation. I want all right. So it turns out I'm going to solve for q0 and q dot 0. So q dot 0 looks like that's going to be negative u of t. It's a little bit weird in my notation here. I'm saying that the initial conditions are moving backwards. I hope it's the equations are simple enough. I hope it's okay. And q0 of t had better be. It turns out to be 1/2 ut squared. So q dot of t is negative u of t. Add those together. q0 is going to be 1/2 ut squared. Okay. If I solve for t, solve out t. In this case, u is 1, so t, let's say, is just negative q dot. So q of 0 is just 1/2. Let's keep that as just 1 t squared. Q dot 0 squared. If I plot that, what I've got in my state space, q dot, is a manifold of solutions, okay, which starts at 0, and then I said that I did this for u as positive, okay. And it goes like this. Okay. This one's not a solution. Where did I get that out? One of my assumptions here, when I inverted t or something, then that solution disappears. That's not a reasonable. You can't have negative time. Okay. Okay. So, in fact, in my notes, I did it. I solved for the other t, which would have been better. Sorry. Okay, so there's a line of solutions here, which if I started this q, so this is actually the positive q, negative q velocities. I hit the brakes. I go coasting into the stop at the origin. Right? Turns out if I think about the negative q case, I get a similar line. Similar curve, it's just this quadratic curve over here. Okay. This is the, you know what, let me be a little bit more careful. Let me make that one pink, because this is the now u is -1 case. Okay. Good. Okay. We figured out the line of solutions where if I hit the brakes, they get to the origin. What do I do? Harness your intuition again. What do I do if I'm here? Right. I want to. So this was the, stopping all the way to the goal. So pretty much, if I'm anywhere else, I want to accelerate. So what does accelerating look like when I'm here? It's going to put me going up. Okay. And what happens is, anytime I'm sort of below this curve, I'm going to drive myself up. I can't go backwards like that. I'm going to drive myself up, hit that, and ride it in. Okay. And if I'm above the curve, what do I do? I have to overshoot a little bit, right? I can't bend down more than this. So I'm going to ride it all the way over to here, connect up to this surface, and write it in, right? Okay, and it turns out anytime I'm over here, the best thing to do is to, did I get my colors wrong? I got my colors wrong. This should be the same action as, let me fix that real quick, sorry. This is the, that's confusing. This is the accelerate, right? And then brake. And this is the brake, right? Which way is it? Yeah, this one should, let me just recolor it for you to make it a little more clear. Sorry about that. So let's say I'm pink over here, blue over here. Okay, then I want to be pink. I want to decelerate just like this if I'm above it, right? Because I want to take these curves that are almost there, right? And if I've got extra time, I'm going to accelerate to the point where I decelerate again. So down here should be blue. And then this is again the case where I decelerate as much as I can until I take the pink line in. Okay? This was the U equals -1, and this was the U equals +1. Okay? Is that at all satisfying? We can now connect this back again to your phase plot pictures, right? We had our initial lines that looked like this, right? I'm allowed to apply a bounded amount of torque, right? So the best thing I can do if I'm right here is I can warp this thing down to the point where I get right there. Okay? And if I'm here, I can warp it up to push me here and then write it down. The hard part is actually showing that that's optimal. And the reason I'm going to go through it is because it forms the basis for all the algorithms that are going to be more general. Okay? So let me show you that that's optimal. To do that, I need to introduce our first sort of optimality ideas for the course. Are people okay with that picture?
Bottom right, below the line. Why do we overshoot?
So tell me where, bottom right? Okay, so here, so this is the place where if I decelerate, I get to the origin, right? If I'm here, then I have a little bit more velocity in the same position, right? So if I hit the brakes, I'm not going to stop in time, right? So I don't quite decelerate fast enough to get here because there's limited torque. So I just slip past it until my chance to come in the other way again.
So these two regions are being separated by Q0 line?
The only separation is that curve.
But on the top left?
Everywhere up here you want to be top left, you said?
Yeah, on the top left and bottom, like below the line, you said you're fine.
Here you're blue. You actually want to, the same way, you want to accelerate as much as you can because you want to get to the place where you have to hit the brakes, right? So this is what? This is me. I'm at some position. I don't have enough velocity that I have to just hit my brakes. So I'm going to gun it until I'm at the velocity where I just have to hit my brakes and then ride it in, right? Up here, I'm at the point where I have too much velocity. Even if I hit my brakes, I'm still going to overshoot a little bit, which means I'm going to have to, and so you could think of it as now, the word brakes maybe flips when you flip that across. Maybe that's the right thing. But the action I take, is only changing based on that switching surface, okay? Which, as you know, will be a nightmare for a lot of our reinforcement learning algorithms. This is a hard cusp, okay? So in general, these So if you have a control system that has a hard nonlinearity like this, which is, I'm doing one thing here and I'm immediately at some discrete place doing a different thing. Okay, that's a very nonlinear event, and it's hard to get analytically when you're doing something more complicated than a double integrator, and it can be hard to get computationally. But we'll talk about that when the time comes. Okay. So how the heck do I make an optimality argument about this? Okay, I want to introduce Pontryagin minimum principle. Okay. This is going to be a load of equations real quick, and we're gonna tease them out. Okay. In general, optimal control problems are going to be formulated by designing a cost function. Okay. That cost function is some scalar quantity that I want to minimize. Okay. So I'm going to use J for, let me I'm going to use the symbols G of XU as an instantaneous cost function. Okay. I'll use H of X to mean final costs. I'm going to show you what this means in a second here. And I'm going to use J of X to be a cost to go. Okay. It's very important. All of these are scalars, not vectors at all. Just a scalar quantity. Okay. So a typical optimal control problem will be formulated as something like h of x capital T plus integral from 0 to t g of x u dt subject to x dot of t is f of xu, let's say the dynamics, and x0 of t is some, let me call it x naught here, x naught. This is a general cost function, sort of cost to go function form for optimal control. We're going to use it a lot. Okay. There's just a couple things to note about it. So just to get some intuition, so g of x, u, that says that's things I'm penalizing throughout the trajectory. So maybe maybe I want to do small actions in general, in which case I could put some term in here which penalizes me for having a u. I could put a u squared in here or something like that, right? Or maybe I want to just worry about being a long way from the origin. Maybe I'll put an x squared in here or something like this, okay? H is a final cost. That's only going to penalize, it's some function that only penalizes the final state of the system. So maybe I don't care what I'm doing for the first capital T seconds, but at time capital T, I want to penalize it for being away from 0, x squared here or something like that. There's lots of different forms. The only thing that's really important to note about this, the only really restriction in the forms that you can play with, is that we do tend to assume this form, which is additive, it's integrable, integrates some scalar cost g. Okay, so I don't look at multiplicative contributions from x at time 1 and x at time 4 or something like that. I'm only looking at additive cost functions. And that, assuming that form, that additive cost form, will make all the derivations work, roughly. Okay, so for the minimum time problem, what is that form? You can formulate it a couple different ways. I could actually just have, in this case, I could actually have g of x u equals 1, right? And have capital T defined as the time and have h of x equals 0. Right, that's a perfectly reasonable optimal control formulation. Okay, so it certainly fits in this sort of general optimal control form. Okay, so now we need to know how to, we've got this guess. I'm going to leave that hard-earned picture up there. I like this one too, but. Pontryagin, let me just say what Pontryagin minimum principle is first, and then we'll make sure it makes sense. Okay, so for this general form, j of x is h of xt plus integral from 0 to t g of xu dt, subject to, and I'm going to try to be very careful about writing these all every time. Let's assume, to begin with, capital T is fixed. Just a parameter somebody chose. And I'm going to, let's say U is bounded to some set U. In our problem right now, it was -1 to 1, right? The minimum principle goes like this. We're going to define this new auxiliary function, Hamiltonian, capital H. Okay. If I have found some optimal control solution, I'll think of it in terms of the solution right now in terms of a trajectory, which is some sequence x star of t, u star of t. Then it must satisfy the following conditions. First of all, we know it must satisfy f of x star u star. that was already one of our conditions. And it has to satisfy the okay. There's a significantly less trivial one, which is that P dot of T has got to equal to negative partial H partial X evaluated at X star, A star, P, which if H is what I had up there, works out to be partial G partial X plus partial F partial X transpose P of T. And this auxiliary variable that we had has to be the gradient of partial H evaluated at X star T. One last condition. This is sort of 1, 2, 3. U star T had better be the argmin over U of H of X star U P. Okay, sorry. Got that out. We're going to make sense of it now. But. Okay, before we derive it, and I'll just do a sketch of the derivation, but before we derive it, let's just think about the implications. Okay. First of all, this says the optimal control trajectory must satisfy, which means it's a necessary condition for optimality. If I found some optimal trajectory X star U star, some trajectory X U, I can verify that a necessary condition is that all these things are hold, but that's actually not a sufficient condition in general. Okay, for linear systems that are convex, linear dynamics that are convex in the cost function, it turns out it's okay, but in general, it's not always sufficient. And it says that if I take my x and I integrate it forward in time, solving x by integrating my dynamics forward, and then I take this other function, this new set of variables, p, which happens to have the same size as x, we'll see that, and integrate it effectively backwards in time because I have a final condition on p. If I do both of those things, and I can write down u as being the argument of what's left, h x, then I've satisfied a necessary condition for optimality. Okay, let's try to make sense of that. How many people have done optimization before at all? How many people have seen Lagrange multipliers before? Okay, good. So let me say a few things, but not dwell. And there's a lot of information in the notes, as fast as I can type. All right, in general, what I'm trying to do is I'm trying to minimize some function. In this case, I'm trying to minimize j, right? I'm trying to minimize this j of x by finding the U tape which minimizes that. Okay? But let's make it a little simpler just to make sure we get the basic idea. Let me just say J is some function of some parameter alpha. I'm trying to minimize J, some function that depends on, I can even do it even simpler. Let's just say minimize over X, J of X. Okay? So if I have some function of X, J of X, looks like this. I want to find the minimum. The first condition, the necessary condition, is that at the minimum, the derivative of that thing better be 0. Yep. Okay? So I can check by just checking if partial J, partial X equals 0, right? Then I've got a candidate, I've got a necessary condition for a minimum. Okay, that's actually a lot of it. The second part is the Lagrange multiplier part. Now let's say I have, let's say X is a vector now, a two-dimensional vector. Let's say I want to do the optimization min J of X subject to the constraint that X1 equals X2. Or X1, let's do something slightly more interesting. X1 plus X2 is 3, okay? Turns out, thanks to the method of Lagrange, one of his many methods, solving this problem is sort of no more difficult than solving this problem, finding necessary conditions for this problem, right? By just making an augmented function, you can now minimize X and lambda of J of X plus lambda times this constraint, which in this case is X1 plus X2 minus 3, has to equal 0. It turns out if partial J partial lambda equals 0, then that means the constraint is enforced. Right? Partial J partial lambda in this is X1 plus X2 minus 3. If that equals 0, which is the condition I'm looking for anyways for the minimum, then I've now not only have I sort of satisfied my constraint, but the remaining minima, the minimization of this, is this constrained solution to that optimization. Okay? If the Lagrange multiplier method is very, very useful. If you don't know it, look it up. It's very good. Yeah?
So in the partial J partial lambda, that J in the partial is this new J.
Oh, sorry. Thank you. Thank you. Yep. Good catch. Good catch. Thank you. Partial of, I don't know, that whole thing. Partial lambda. Thank you. Good catch. And in the method of Lagrange multipliers, sort of lambda has an interpretation as sort of a constraint force. Okay. What you're about to see is that all I'm saying in Pontryagin minimum principle, which is, an absolute sort of staple in optimal control, is all I'm saying is that J of X is, which is my cost function, my cost to go function, is at a stationary point with a Lagrange multiplier which enforces this dynamics. Okay? And that Lagrange multiplier happens to be P. Okay? So let's just see how that plays out. Okay, so this is a sketch of the derivation of Pontryagin minimum principle, which I think I'm just going to do enough so you see where those things are and have some intuition about them. A sketch of it based on the calculus of variations. There's many other ways to do it. The calculus of variations, which is a scary name for a very simple thing. Okay. This is the problem I'm solving. J of x0 is h of x plus g integral over g, subject to those constraints. Okay? So how do I write that in terms of a Lagrange multiplier? I'm going to do a second function, which I won't make the mistake of calling j again here. Let's call it s. Some function s is going to be h of x t plus the integral from 0 to t of g of xt ut plus some Lagrange multipliers, p in this case, times my constraint, which is x dot minus f of xu. I was trying to use t's everywhere. Let me try to keep using t's everywhere. Okay, so now I can explicitly try to find the place where S, which is my Lagrange multiplier version of my problem, which has the explicit cost that I'm trying to minimize, subject to the constraints that X better be satisfy my dynamics. Okay, exactly the same as that 2-second Lagrange multiplier introduction. Okay. Now getting it right is a little bit funny. So S is now, you could think of S as a functional, right? A function of functions. If I take a variation, this is just, it's going to be exactly like your basic calculus, but the calculus of variations uses these symbols for a variation on a function. Is just going to be partial h partial x times the variation in x of t plus the integral 0 dt. Notice quickly that this thing inside here is just h, right? That's my Hamiltonian. So that thing inside there, I can just okay, this says, this is a variational analysis of S that says if my function changes by some small amount in x tilde, this is the result in changing S, in S. Similarly, if my thing changes by a little bit in xt, or in ut, or in pt, or in all of them simultaneously, this tells me what the variation is going to be in S. Okay? The stationary conditions then, if I'm at an optima, what I care about is that if I change u a little bit, if I change x a little bit, if I change p a little bit, S better not change. That's my condition, my necessary condition for optimality. Okay? So what's, if partial h, partial p is 0, then I know that changing p isn't going to change the solution. So I can look for stationary points with respect to p. Partial h, partial p better be 0. What's partial h, partial p? Well, it turns out it's just x dot minus f of xu, which is my forward dynamics. Okay. So if I've integrated my system forward in time, then this thing's going to be true, and and a steady state with respect to changes in P. Okay. Okay. Let's look at the changes with respect to x. So to get the contributions from x correct, we first need to worry about this x dot. We don't want to have that x dot floating around in there, so let's integrate by parts to get that out of there. Okay. We're going to look at this partial x, the variations, but first integrate by parts. So if the integral of my p of t x dot t dt from 0 to t is just going to be p of t x of t minus p of 0 x of 0 minus the integral from capital T of p dot t x of t. I forgot my transpose. dt, right? Basic integration by parts. Okay, if I now take my variation in partial x, having used that, then what I get is gives me which in this case was partial g partial x transpose plus partial f partial x transpose p of t. My goal is to show you enough of the derivation that you understand what these terms are and not so much to get completely bogged down in it. If you want a good treatment, a careful treatment, you should see Bert Sekas' Optimal Control book. When I say careful treatment there, it's going to be 5 pages or more, at least. Okay, so Pontryagin minimum principle says that if my constraint is satisfied to x dot, and if I can just integrate back this p dot backwards in time from some final conditions, which are the same basic variation argument that drives this, okay, then I found Lagrange multipliers, which satisfies that constraint. Okay, and the final variation says that u had better be the minimum of h of x. That puts me at a local minima in my constrained optimization. Okay? Big pill to swallow, but this is the way we're going to show that the brick solution is optimal. People are much more enthusiastic when there's bricks. Okay. It's okay. I understand. Okay, so let's turn the crank and use this tool now to see what the heck, see if we can verify our original bang-bang policy is optimal. So for the bang, let's see, Pontryagin on bang double integrator. What's the Hamiltonian look like for this thing? G of xu, we said was just 1. Okay. Then P transpose times x dot minus f of xu. I'll just write it out in element form since it's so simple. It's P1 times q dot plus P2 times u. Okay? So let's, if we had derived our bang-bang controller just like this, then we could actually immediately say, what's the optimal control solution? If I want to take U star is the argmin U in -1 of 1 of H XU P. And what's it going to be? Just looking at what I've got on the board here. This is a good time to make sure you get it. Yeah, good. So these terms have no impact, right? If P2 is positive, and I want to minimize this thing, then U better be negative, right? As negative as possible. It's negative as possible means -1. And if P2 is negative, then U should be as positive as possible to minimize that thing, okay? So it turns out our same policy that we worked hard for in the Pontryagin, in terms of the Lagrange multipliers, works out to just be P2, sine of P2 of t. Negative sign, sorry. So the sine function is just 1 if it's greater than 0, -1 if it's less than 0. My equations for P, which if I didn't use the word adjoint equations yet, I should have. These equations for P are called the adjoint equations. My equations for P are pretty painless, right? So P1 dot is negative partial h partial x1. x1 is q, so it doesn't appear at all. That's 0. So that Lagrange multiplier isn't going to change at all. That's pretty painless. And P2 dot is negative partial h partial x2, and that's negative P1 t, right? Okay. So it turns out that P1, my Lagrange multiplier is just going to be some constant. And P2, T is just going to be the integral of that constant. C2 plus C1 times T. Okay. Trying to debate how much to squeeze into the next few minutes. You know what? Let me do it tomorrow for real, or on Thursday for real, because it's going to take 10 minutes to finish, but it's worth it doing it right. So, for homework to yourself, see if you can work it through. Take the equations that we had, and show that those 4 conditions are satisfied. And I'll spend the first 10 minutes of class doing it properly on Thursday. I don't want to rush through it and have it mean nothing. Okay? Sorry, I wrote 3 here. There's a final condition on P2, so 3 conditions by this numbering. Awesome.